Rajni Sir's chemistry tutorials. In the first lecture, I have discussed about few basic laws of chemistry. I got quite a good review about that, and so it has inspired me to continue this channel with a full heart. Earlier, I was a little bit nervous because that was my first video. Now I am feeling much more confident than earlier. So now I am continuing the same lecture, same chapter, some basic concepts of chemistry. Here we'll talk about few more laws, for few more concepts. Plus we'll also discuss today mole concept. So let's first start and we'll first discuss Avogadro's law. What is Avogadro's law that we are first going to discuss? Avogadro said that equal volume of all gases will contain same number of particles. The gas may be of anything. The gas may be hydrogen gas, gas may be oxygen gas, gas may be ammonia, carbon dioxide, whichever gas you take doesn't matter. If you take same volume of these gases, then these volume will contain, same volume of each gas will contain same number of particles. Volume, suppose you are taking 1 liter, take 1 liter for each and every gas. Keep temperature and pressure same for all these volumes. Okay, so if all gases are at the same temperature and same pressure, then equal volume of these gases will contain equal number of particles. This is called Avogadro's law. Equal volume of all gases will contain equal number of particles in identical conditions, or if the conditions, that is temperature and pressure, are kept same. If external conditions, that is temperature and pressure, are kept same. Avogadro's law. Equal volume So this is the law which states that equal volume of all gases contains equal number of particles. Equal volume of all gases contains equal number of particles. If all the external condition, that is temperature and pressure, are kept constant, then so this law is applicable only for gases, not for solid, not for liquid. Just remember that, because if you are using this thing for liquid or for solid, it won't be applicable. Gases have a particular pressure at a particular temperature. That is because of the movement of particles and collision of these particles with the walls of the container. So if there is a lighter particle, then at the same temperature it will move faster, but heavy particle will move slowly. So when you are keeping temperature constant and number of particles are same in the containers, same volume of containers, if the number of particles are same, then their mass and their velocity will try to compensate each other so that they will maintain same pressure. If you change anything, like if you change temperature, if you change pressure, any one thing, if you change it, then in that case law won't be applicable. If the number of particles is changed in the container, pressure or temperature will get different. If you are keeping different temperature, then the pressure will be different. So if any one of them you are changing it, then this law won't be applicable. So this law states that equal volume of all gases in identical conditions will contain equal number of particles. This is called Avogadro's law. I give you simple examples for it. So see few examples. Example. If I take it here, suppose it is a any vessel which has a volume of X liter, and if I keep in this volume, in this container, if I am keeping it here, suppose hydrogen gas, then it will be, suppose it will be having a n moles of hydrogen. Then if I take, and its temperature and pressure are kept constants, and T and P will be constant. Whichever volume I am going to take, in all those volumes, the temperature and pressure which is over here, that will be same everywhere. So if I am taking it here also, one more vessel which have the same volume, that is X liter is its volume, and now I am taking it here O2 gas, then it will contain n mole of O2. If I take it here carbon dioxide in this CO2, then if it is X liter, it will again contain n mole of O2. Here, this condition, don't forget to write that temperature and pressure is same in all these cases. If I am taking it here, suppose, if I am taking it here, instead of this, if I take it here sodium vapor, so this is also a gas, and if this container's volume is again X liter, then it will contain n moles of sodium vapor. If I take it here, suppose I am taking it here water vapor, H2O vapor, in X liter of the container, then it will have n moles of, actually it is supposed to be n mole only, because mole is a unit, so no need to write moles, okay? Like we generally write kilograms, but kilogram is a unit. So if it is 1 or 10, doesn't matter, we write kilogram only. Kilograms is actually not appropriate. So n mole of H2O vapor. So it doesn't matter what gas is over there. You may have a sodium ions over here, or like suppose I am taking it here Mg2 plus in the gaseous form. Then in that case it will have X liter of containers here. So n mole of Mg2 plus gas or vapor, we can have it here. So it does not matter what you are taking it, any atom, molecule, even if you take it here, suppose nitrogen atoms, okay, nitrogen atoms, so gaseous form, X liter, so n mole of nitrogen atoms. Nitrogen gas is a different thing, N2 will be different thing, and nitrogen atom is different thing. So it doesn't matter whether it is atom, molecule or ion, but if you are taking same number of moles, or you can say same volume of the container, it will contain same number of particles. Whether it is atom, molecule or ion does not matter. Okay, this law is called what? Avogadro's law. So it does not matter whether it is atom, molecule or ion, but equal volume of all gases would contain equal number of particles. Whether it is atom, molecule or ion does not matter, but it is applicable only for gas. It is applicable when the temperature and pressure are kept same. Not applicable for liquid, not applicable for solid, only applicable for gases. Okay, that's it about the Avogadro's law. Now we'll see Gay-Lussac's law of combining volume of gases. Gay-Lussac's law of combining volume of gases states that whenever two or more gases will react with each other, their volume bears simple whole number ratio with each other, as well as with the volume of product if gas, when the temperature and pressure are kept constant. This law was given by Gay-Lussac, so that's why it is called Gay-Lussac's law of combining volume of gases. So Gay-Lussac's law of combining volume of gases, when two or more gases reacts, their volume bears simple whole number ratio with each other, as well as with volume of products if gas, when external conditions are kept constant. This law is said to be Gay-Lussac's law of combining volume of gases. Now, this is very simple. Once you have understood Avogadro's law, then this law is very simple. Why it is very simple? Because Avogadro had already said that equal volume of all gases would contain equal number of particles if temperature and pressure are kept constant. Even this law says that temperature and pressure has to be kept constant. Now see what is happening. Suppose I am reacting hydrogen and oxygen to form water, but water will obtain in vapor phase. If the temperature is kept higher than 100 degrees Celsius, then the water formed will be in the vapor phase, not in the liquid state. And I want to see the relationship. In. So this law is very simple because equal volume of all gases contains equal number of particles, which was already told by Avogadro. Now this law is just telling you the volume relationship. So they are forgetting about the number of particles. They are telling you that volume relationship is what between the combining gases. So it's very simple. You can easily prove it in this way, that they are saying according to Avogadro, Gay-Lussac's law, it's a 2 volume of hydrogen will react with 1 volume of oxygen to give you your 2 volumes of water vapor at constant temperature and pressure. See, the condition for this reaction is that whenever you have 2 molecules of hydrogen, you should have 1 molecule of oxygen, then you will get 2 molecules of water vapor. If I take 2 volume of this hydrogen gas, then automatically it will have twice the number of oxygen, because oxygen's volume I have taken 1 volume and I am taking hydrogen's volume to be 2 volume. Suppose it is 1 liter. If I take 1 liter of oxygen, I will be taking 2 liters of hydrogen. So automatically 2 liters of hydrogen will contain twice the number of molecules of oxygen present in 1 liter of oxygen. Because if you double the volume, number of particles will get doubled. According to this reaction, you need to have twice, number of hydrogen atoms should be twice the number of oxygen atom. So when you have same temperature and pressure, so according to Avogadro's law, 2 volume of hydrogen will contain twice the number of hydrogen molecule than present in the 1 volume of oxygen. So it is very common, very easy. It's not a big deal. So twice volume of hydrogen we have to use, 1 volume of hydrogen oxygen we have to use, 2 volume of hydrogen, 1 volume of oxygen I have to use. I'll be getting 2 volume of water. Suppose volume, you may say, what is this volume? So if I take it here, 2 ml of hydrogen, I will be using 1 ml of oxygen and I'll be getting 2 ml of H2O. So 2:1:2 ratio, you will be always getting it. Suppose I'm taking it here 2 liter, I will have to take it here 1 liter and I'll be getting it here 2 liter of water vapor. So it will be always, volume ratio will be always 2:1:2. Number of particles ratio should be 2:1:2, which will be automatically maintained if you take the volume in the ratio of 2:1:2. Because Avogadro has already said that equal volume of all gases contains equal number of particles. So if I double volume, then the number of particles will also get doubled. If I half the volume, number of particles will become also half. And I have to maintain ratio of number of particles 2:1:2. So if I maintain the ratio of volume in 2:1:2, number of particles will be automatically 2:1:2. So that is the only thing that was Gay-Lussac had said. Avogadro said almost same thing, but he did not say anything about the volume while reacting gases. But Gay-Lussac's law says something when gases are reacting, then what will happen, what will the relationship between their volumes, that he said. Now this makes your calculation slight easier. Instead of going to find out mass or number of moles, suppose gases are reacting, it will be easy for you to predict that how much amount of gas will be needed for a reaction, how much amount of product will be obtained. You can easily obtain by this law. So this law is also very important law. Okay, that's it about the law. let's see one problem where we'll be asked that what will be the volume of this particular substance, either formed or the particular gas, how much it will be needed. So I just give you one example. Example, nitrogen, it's supposed to react with hydrogen to give you your ammonia. So first of all, you need to balance it. It is a gas, this is also a gas, and this ammonia is also a gas. If you balance, you will have to put it here 3, here you have to put it 2. Now, you will be given that nitrogen's volume is suppose x ml. Instead of taking x, y, z, I am taking a particular volume of nitrogen. Then I will be trying to find out what volume of hydrogen will be needed for the reaction and what volume of ammonia will be getting produced. So, if volume of nitrogen gas be 100 ml, then what volume of H2 is needed for the reaction? Needed for the reaction. What volume of NH3 will be formed after the reaction? This is the question. What volume of ammonia will be formed after the reaction? So here N2 is reacting with 3H2. This reaction will be given to you, or you already know the reaction, so you can just write it down. So when it is one volume, it reacts with 3 volume to give you 2 volumes of ammonia. So 1 volume of N2 reacts with 3 volumes of H2. So 100 volume, 100 ml I have taken. So 100 volume, instead of 100 volume, you can write 100 ml of N2 will react with, it's a unitary method. So 100 volume will be reacting with, so 100 ml of N2 will react with X volume of H2. So X will be equal to unitary method. So it will be equal to here 1 into 3. Sorry, it will be here 3 into 1. 100. 3 into 100. X into 1. So diagonally you have to multiply this X and 1 you need to multiply, that will be equal to 100 into 3. So X into 1 will be X only. So 3 into 100 will be 300. So 300 ml of H2 will be required. Now the question comes, question is also asking what volume of ammonia will be produced. So when you have 100 ml of 1 volume of nitrogen, 2 volumes of ammonia is needed. So volume of ammonia formed, volume of NH3 formed will be equal to 1:2 ratio it is having. So it will be here 2 into 100 ml. That is 200 ml of NH3 will be formed. So it's a very easy to calculate all these things. So we saw that it is very easy to calculate all these volumes. What volume will be reacting, what volume will be produced. Instead of going to calculate it in moles or in grams and then coming back to volume, this will be quite a lengthy method. So if you have been given some volume of gases, then volume of other gases you can easily calculate. What volume of other gas will be required for the reaction, what volume will be produced after the reaction, you can easily calculate. This is main application of Gay-Lussac's law. Okay, that's it about Gay-Lussac's law. We'll see now mole concept. Now we'll see mole concept. What is a mole? Actually, it is a fundamental unit of amount of substance. Fundamental unit of amount of substance. We have got total 7 fundamental units that you would have studied in physics. So I'm not going to discuss about that. You can study in physics. So we are discussing here mole. So what is a mole? Mole is a number. Certain number was called 1 mole. Like just like we call that 12 pieces will be called 1 dozen. Similarly, 6.022 into 10 raised to 23 particles, entities. Entities, particles means it could be atom, it could be molecule, or it could be any ion. So 6.022 into 10 raised to 23 particles or entities will be called 1 mole. Wherever you see that there are 6.022 into 10 raised to 23 particles, you will say it is 1 mole. 1 mole could be any substance, that it could be like hydrogen atoms, hydrogen molecule, it could be hydrogen ion, H plus ion, it could be H minus ion, it could be anything. We'll call it here 1 mole if it contains 6.022 into 10 raised to 23. Now, since dozen is very familiar to you, so you will quickly understand what is 1 dozen. But mole is a new thing for you, so you may be thinking, what is a mole? What is this? They are talking about mole. It's not a big thing, it's a very simple. Just like a dozen you can treat it, so dozen means 12. Similarly, 1 mole means 6.022 into 10 raised to 23 particles. That's it. Nothing more than that you have to worry about. It's a very simple thing. See, like you might hear a word like gross. So you will say, what is a gross? Okay. So suppose somebody has not heard what is a gross, then they will be thinking, okay, such a big thing or something could be there, which is like he will be wondering or she will be wondering, what is this actually gross? And once you tell that it is nothing but 144 substance will be there, that we call 1 gross. So just like a dozen, it's a gross. So in dozen you have got 12 pieces. In 1 gross you have got 144 pieces. That's it. Similarly, in 1 mole you have got 6.022 into 10 raised to 23 particles. Particles could be atom, molecule, or ions, right? So this is 1 mole. Some people also ask me that from where this number came, 6.022 into 10 raised to 23 particles only, why they have chosen it. So I tell you in brief about it. Actually, our atomic mass unit is carbon, that we are going to discuss just after this. So atomic mass unit is nothing but carbon. It's 1/12 part of carbon 12 atom is considered to be atomic mass unit. When we take 12 gram of carbon 12 isotope, it contains 6.022 into 10 raised to 23 atoms of carbon. So they said that any substance which will contain as many atoms of carbon is present in 12 gram, that many particles, then it will be called 1 mole. Any substance which contains as many particles, as many atoms of carbon is present in 12 gram of carbon 12 isotope will be called 1 mole. Since carbon 12 was present, the number of carbon 12 atom which was present in 12 gram of carbon 12 isotope was 6.022 into 10 raised to 23. That's why this number was only given as a 1 mole. So it's a simple thing, but you don't have to worry about that, why this number was given. Now you just need to remember only this much, that 6.022 into 10 raised to 23 particles will be called 1 mole. Okay, that's it. Nothing more than that you need to understand. Any substance which contains 6.022 into 10 raised to 23 particles is called 1 mole. So just like a dozen, it does not matter what substance we are talking about. We'll be only talking about 1 mole means 6.022 into 10 raised to 23 particles. Like suppose if I say that 1 mole of H2. So this means that it is 6.022 into 10 raised to 23 molecules of H2. If If I talk about 1 mole of hydrogen atom, okay, sometimes they may not say H2 like that, they will say hydrogen gas. Gaseous hydrogens are made up of H2 molecules only. So 1 mole of hydrogen gas is nothing but 1 mole of hydrogen molecule. 1 mole of hydrogen atom means 6.022 into 10 raised to 23 atoms of hydrogen. Atoms of hydrogen. Atoms of hydrogen I am just writing so that you will not get confused. Hydrogen. If I talk about 1 mole of H plus ions, that means 6.022 into 10 raised to 23 ions of hydrogen. If I talk about 1 mole of H minus ion, that means it will be having 6.022 into 10 raised to 23 ions of H minus. So it does not matter whether it is a positively charged, negatively charged, or whatever it is. 1 mole of any substance will contain exactly 6.022 into 10 raised to 23 atoms, molecules, or ions. This is called 1 mole. So 1 mole we came to know, this is a fundamental unit of amount of substance. This will be only used in chemistry for quantity of substance. That's why this is very important part. You must remember what is 1 mole. So now we'll discuss atomic mass unit. Atomic mass unit is needed because hydrogen's mass is very small in comparison to gram. So if you try to express mass of an atom in gram, it will be highly inconvenient. So we need some other way to express mass of an atom. Now the mass of atom could be expressed in terms of any other atom's mass. So in the beginning, first hydrogen was chosen as a standard mass. Due to certain reason, hydrogen was later on discarded. Then oxygen's 1/16th part was chosen as a atomic mass unit. Later on, that was also discarded due to some problems. Let it be. Now what we are using it is atomic mass unit is 1/12th part of carbon 12 isotope. So now atomic mass unit, if we are talking about, that means we'll be taking 1/12th part of carbon 12 isotope, and this is called atomic mass unit. Whenever you compare mass of any other atom with 1/12th part of carbon 12 atom, then whatever number of times mass of other atom you are getting it in comparison to 1/12th part of carbon 12 atom, that we call atomic mass of that particular atom. I will give you an example for it also. First let me write what is atomic mass unit. Okay, atomic mass unit. It is the mass of 1/12th part of carbon 12 isotope. When we are talking about what is atomic mass unit, then we'll be taking carbon's mass, one carbon atom's mass, and we'll divide it into 12 equal parts, and one part of this will be called atomic mass unit, which we also called it 1 AMU, or we just write 1 U. So 1 AMU is equal to 1/12th of carbon 12 mass. So it is the mass of carbon 12 isotope. Now carbon 12 isotope, we need to say it, because if I don't say, if I just say it is a carbon's 1/12th part, mass of 1/12th part of carbon 12 atom, carbon atom, just not carbon 12 atom, then in that case it could go wrong. Now you may ask why it is. Because carbon has got 3 isotopes. Your unit should be well defined. If I don't say it is carbon 12 or carbon 13 or carbon 14, somebody might take carbon 13 isotope, even though the most abundant form is carbon 12. But by chance, if they are taking it carbon 12 instead of carbon 12, carbon 13 or carbon 14, then they will divide into 12 equal parts. They will get different mass. When they are comparing with that mass, any other atom's mass, obviously we will be getting wrong answers. So we have to be very specific about unit. So unit is 1/12th part of carbon 12 isotope. When you compare this mass with any other atom's mass, if that atom's mass is 4 times, 10 times, 20 times, accordingly their mass will be. If suppose I take an example of lithium atom. then lithium's mass is found to be 7 times of the mass of 1/12th part of carbon 12 atom. Okay, so lithium's atomic mass is said to be 7 AMU. So if I take it here, one atom of lithium, then it was equal to 7 times of the mass of 1/12th part of carbon 12 isotope. So it was said to be 7 AMU, atomic mass unit, or you can just write U also. U in respect of Dalton, it is read as Dalton, U, atomic mass unit. If I say the mass of one atom of helium, helium's one atom's mass was found to be 4 times of the mass of 1/12th part of carbon 12 isotope. So helium's mass will be 4 AMU. And these masses are called relative atomic mass. They are not absolute atomic mass. Relative, why it is said? So you can say that since these masses are actually obtained when it is compared with the mass of carbon 12 isotope or carbon atom. That's why it is called relative atomic masses. When you express these masses in grams, then in that case that will become absolute atomic mass. Okay, so just you have to write any atom's mass. If they will ask you write mass of any atom, we write in terms of carbon's mass, because carbon is the basic unit or fundamental unit chosen to compare atomic masses of other elements. Okay, so that is our standard right now. So 1/12th part of carbon 12 isotope will be considered to be the standard atomic mass, which is called 1 AMU. Any atom's mass will be compared with the mass of 1/12th part of carbon 12 isotope. Now see one more thing over here. It's atomic mass unit. Whenever you have to find out molecule's mass, then molecule will contain certain number of atoms in it. These atoms have their own masses. If you add all these masses, you will be able to get molecular mass. So what is molecular mass? Molecular mass. It is the sum of atomic masses of the elements present in the compound. It is the sum of the atomic masses of the elements present in the compound. As for example, if I take molecular mass of H2O. So we already know that the mass of one hydrogen atom is 1.008 gram, but let that be 1 AMU it is actually. So what we can do it here, mass of hydrogen atom is 1, total number of hydrogen atom is 2. So we can multiply this by 2, and mass of one atom of oxygen is 16 AMU. So I can add 16. 16 plus 2, 18. So it will become 18 AMU. So this is becoming here molecular mass of water. Similarly, if I have to find out molecular mass of carbon dioxide, CO2, take the mass of carbon, that is 12, mass of oxygen, that is 16, but there are total 2 atoms of oxygen, so we can multiply this by 2. So 1 atom of carbon, so just 12, 2 atoms of oxygen, so 16 into 2 I did. Total it is becoming 12 plus 32, that's equal to 44 AMU. One more thing I would like to specify, and you must remember it. If they will ask you atomic mass or molecular mass, you will write as AMU. If they will ask you molar mass, you will write in gram per mole. Okay, once again I am telling you, if you are writing atomic mass or molecular mass, you will write it as AMU. Whenever they will ask you to write molar mass, you will write it as gram per mole. So unit you should not forget to write, because sometimes you will lose your marks just because of not writing the unit. So molar mass of H2O is equal to 18 gram per mole. Molar mass of CO2 is 44 gram per mole. But if they will ask me molecular mass of H2O, I'll write 18 AMU. If I will be asked molecular mass of carbon dioxide, I will write 44 AMU. But when molar mass is asked, I will write 18 gram per mole, 44 gram per mole for carbon dioxide. Like this we are supposed to write. So we saw what is atomic mass unit. How will you compare with that? There is one thing that is called isotope. Isotopes are atoms of same element having same atomic number but different mass number. Now problem comes that whenever any reaction is there, like carbon is reacting with oxygen to give you carbon dioxide, then how will I come to know that the carbon which is reacting over there, that carbon is carbon 12 or it is carbon 13 or it is carbon 14? Just to avoid this type of confusion while calculating masses, we have one more way of doing it in a better way. Take one example. If you take any natural sample of chlorine, then in that case we are getting chlorine 35, which is having a percentage abundance of approximately 75%, and the percentage abundance of chlorine 37 was found to be approximately 25%. So we'll take average of it, and that atomic mass will be used for all type of calculations. For any chemical reactions, we'll be using atomic mass of chlorine, which will be coming as an average of chlorine's atomic mass. So I'll find out average atomic mass. Average atomic mass will be equal to percentage composition into atomic mass. Of the isotope 1 plus percentage composition into atomic mass of the isotope 2 plus dot dot dot, like this, upon all these percentage composition. Percentage of isotope 1 plus percentage of isotope 2 plus dot dot dot, like this. Generally this will be coming as 100%, because some of the isotopes, all types of isotopes, will be always equal to 100%. So that will be able to calculate. As for example, in a natural sample of chlorine 35, chlorine which is having a mass of 35 unit was found to be 75%, and chlorine which is 37 is having a percentage of 25%. So if I have to find out the percentage, if you have been given percentage of chlorine 35 and percentage of chlorine 37, from this we can find out average atomic mass of chlorine. So average atomic mass of chlorine will be equal to percentage of chlorine 35 with 75. So 75, its atomic mass is 35. So I can multiply this by 35 plus atomic mass of chlorine 37 is 25% into 37. This 37 divided by 75 plus 25, and if you calculate it is coming as 35.5. So gram per mole it will become here, or if you write it in AMU, then you can write it as 35.5 AMU also you can write it. So wherever you will use atomic mass, you will be using it as a 35.5 AMU. When you use molar mass, you will use it as a 35.5 gram per mole for any chlorine atom. Okay, so it does not matter that chlorine 35 is present in the reaction or chlorine 37 is present in the reaction. Just you forget about that and use always 35.5 as the atomic mass of chlorine. This is only applicable for all other isotopes also. In case of any other elements, you will be using same method. Now the last part that we'll be discussing now today is that what is percentage composition of any element in any compound. Before going to discuss that, only two things I wanted to discuss, which you already know. What is isotope? So isotopes are atoms of same element having same atomic number but different mass number. Then comes isobars. So isobars are atoms of different element having different atomic number but same mass number. So isobars will have same mass number but different atomic number. Isotopes will have same atomic number but different mass number. So these two definitions you need to remember. Now I am going to discuss here percentage composition. That will be the last part for today. So remaining the concentration terms will be discussing in the third class. Third class will be the last class for this chapter. So let's see percentage composition of an element. Percentage composition of an element is equal to mass of the element in the compound upon total or molar mass, total mass of the compound or molar mass of the compound, you can write molar mass of the compound into 100. Okay, molar mass is nothing but atomic mass or molecular mass or ionic mass present in gram, that is your molar mass. So this is that's it about the formula. Just I'm calculating for a particular element, like suppose for different elements I'm going to calculate it. So I'll just take one example to illustrate this. As for example, find percentage composition of all the elements present in sodium carbonate Na2CO3. Find percentage composition of all the elements present in sodium carbonate. This is the question. It's a question. First of all, you need to find out molar mass of sodium carbonate. So molar mass of Na2CO3. As you already know, mass of sodium is 23. So multiply this by 2 because Na2, there are 2 sodium atoms. So multiply by 2 plus 12 plus 16 into 3. 23 2s are 46 plus 12 plus 16 3s are 48. 48 plus 12 becomes here 60. 60 plus 46 will be 106. So it will be equal to 106 gram per mole. Now we have to find out percentage composition of each element. So one by one we'll find for sodium, then for carbon, then for oxygen. So percentage composition of sodium. So that will be equal to the mass of sodium in the compound upon molar mass of sodium carbonate into 100. So I just write for this element, I am writing the formula. So mass of sodium in the compound or in sodium carbonate into 100 upon molar mass of Na2CO3. Now sodium's mass is 2 sodium atoms, so 23 into 2, that is 46 gram. So this will be here 46 divided by 106 into 100. This is the mass of, this is the percentage of this sodium. This calculation, if you do, it comes at 43.4%. So this will be equal to 43.4%. Similarly, percentage composition of carbon will be equal to 12 upon 106 into 100, and percentage composition of oxygen will be equal to 16 3s are 48, so 48 upon 106 into 100. This you have to calculate it manually. You will be able to get the answers. So all these calculations you can do, you can write it down. The best way to check whether your answer is right or wrong, do one thing: whatever elements you have got it here, their percentage composition you have found it, just add them up. If it comes 100, that means your calculations were correct. If there was some mistake, then this will not add up to 100. Few change in percentage, like a little bit of a small change in the percentage may occur over here. So your exact value might not, you may not get exact value every time. Means it might go slightly higher than 100 or slightly lower than 100. That's fine. But there should not be a change of a certain percent. In decimal, little bit of increase or decrease will be okay. But the total should remain almost very close to 100. More your value is closer to 100, more accurate will be your calculation. So these values are your percentage composition. Similarly, you can take more examples. You can try doing this. This is a very simple thing. You have to take that element's mass in the numerator, and denominator will be the molar mass of the compound multiplied by 100. You will get the percentage composition. One thing about the mole, I just write it down so that you will be able to use it for calculation purpose. You need to try numericals. If you have any problem, you can ask me in the comment box that these problems I did not get. I'll solve that problem. I will put it over there. So first of all, what I'm telling you, just try to remember that 1 mole relationship with volume, with the number of particles, I'm writing at one place. So just remember that you will use it for calculation purpose. 1 mole of any substance, that means it will contain 6.022 into 10 raised to 23 particles. That particles may be atoms, molecules or ions. So it could be atoms or molecules, or it could be ions, which is also equal to 22.4 liters at STP. STP, NTP, more or less it is same. We'll discuss about that. Little bit of a small difference could be over there, STP, NTP. So that we'll discuss in states of matter chapter. So 22.4 liters. And this is if gas. And that's also equal to molar mass of the substance. Molar mass, or you can say molecular, atomic, molecular or ionic mass in grams, that will be better. That is equal to molecular mass or atomic mass or ionic mass in gram. Okay. So 1 mole is equal to 6.022 into 10 raised to 23 particles. Particles means it could be atoms, molecules or ions. That is also equal to 22.4 liters at STP if gas, which is also equal to molecular mass or atomic mass or ionic mass in gram. Okay. So this is your 1 mole. Sometimes you have to change one thing into the other. So this is going to help you. This is very important. That's it for today. Thanks for watching. Learn something. and grow with it. Don't waste time, just study. And if any problem, you can let me know. If you want to understand any other topic or any topic you have not understood, you can let me know, then I can explain that topic once more in a better way. I'll try my best. Thank you for watching. Thank you for giving me time. Thank you. Bye bye everyone. Take care. Be safe.